Structural Audit of RCC Building in Kolhapur City. Abstract: a structural audit is required for framed structures in order to propose suitable corrective actions for all sorts of structural flaws and damages, so that it can continue to meet the requirements for strength and serviceability. A structural audit should be performed at least once every 5 years for any structure. A structural audit should be performed every 3 years for structures older than 15 years. Corrosion and aging appear to be the most common causes of structural member deterioration. Dampness and leakage from slabs, fractures in walls, and other factors cause corrosion in structural elements. As a result, the building's strength and serviceability can be improved by performing the following steps. Slabs for waterproofing. Keywords: RCC building, strength, non-destructive testing, corrosion, serviceability. Introduction. A structural audit. Structural audit is an overall health and performance checkup of a building like a doctor examines a patient. It ensures that the building and its premises are safe and have no risk. It analyzes and suggests appropriate repairs and retrofitting measures required for the buildings to perform better in its service life. Structural audit is done by an experienced and licensed structural consultant. Need of structural audit. Structural audit is carried out in order to 1. To increase life of property. 2. To know the health of building and its expected life. 3. To check actual reliability of the structure. 4. In order to recommend rehabilitation techniques. 5. In order to highlight the critical areas and repair them immediately. 6. For structural audit certificate required by municipality and other authorities. See Structural Audit Bylaws. As per Clause Number 77 of Revised Bylaws of Cooperative Housing Societies, the Society shall cause the structural audit of the building as follows. 1. For building aging between 15 to 30 years once in 5 years. 2. For building aging above 30 YEARS once in 3 YEAR. D. Objectives of structural audit. 1. Performing preliminary inspection of the building. 2. Preparation of architectural, structural plan of the building. 3. Visual inspection to highlight critical area. 4. Performance of NDT tests. 5. E-tabs modeling of the building. 6. Finding actual strength of the building. 7. Suggesting remedial measures. 8. Noting of all visible defects, deterioration, and its quantification. 9. These are marked on floor drawings from which he estimates is worked out. 10. Diagnosis of damages. 11. Suggest remedial measures. 12. Submission of the conditions survey and structural audit report, priority-wise estimate for rehabilitation, condition survey drawings, photographs. 13. Necessity of non-destructive testing will be decided after inspection of structure. Scope of the work. 1. Surveying the premises from the insides and outsides. Each and every premise to be surveyed to get a proper idea of its present structural condition. This physical survey will be carried out with hammer tapping on the RCC members to ascertain the degree of distress. 2. Identifying and noting allied problems pertaining to leakages and seepages and any additions/alterations carried out in the premises, which may be detrimental to the present health of the structure. 3. Identifying the nature of damages, extent of damages and its severity. 4. Carrying out NDT tests at required locations. 5. Analyzing various defects observed, identifying the likely causes of all such damages. 6. Finally suggesting remedial measures to be adopted to restore the structural health of the presently diseased structure with a view to enhance its structural stability and durability as per the priorities required. 7. Submitting detailed survey report containing our observations, suggestions, recommendations, and photographic log. 2. Literature review. Shahi H. has stated structural audit is an important tool for knowing the real status of the old buildings. The audit should highlight and investigate all the risk areas, critical areas, and whether the building needs immediate attention. If the building has changed the user, from residential to commercial or industrial, this should bring out the impact of such a change. This publication gives step-by-step guidelines for carrying out structural audit of old buildings. Monteria.J. Pathak, NJ have estimated the soundness of existing structures whose life has crossed the age of 30 years. Concrete constructions are generally expected to give trouble-free service throughout its intended design life. The deterioration of buildings can bear sold to various factors including fire damage, frost action, chemical attack, corrosion of steel SE. During the lifespan of the structure. The investigation of soundness is thus essential for finding the present serviceability of the structure and its scope for future developments or for the change in its utilization. Balasik J.P., Lawrence S., has stated the management and maintenance of the build-the rightage is one of the main concerns of the owners of concrete structures. Combining NDT methods is currently considered as one of the most appropriate ways to improve the quality of the diagnosis of concrete structures. This paper describes a French project named SENSO, Strategy of Non-Destructive Evaluation for the Monitoring of Concrete Structures, devoted to developing a methodology for the non-destructive evaluation of concrete based on a multi-technique approach. Villain Geraldine Sparta, Zubir Mehdi have implemented non-destructive techniques, NDTs, for surveying concrete structures in marine environments. Non-destructive measurement results must be correlated with concrete durability indicators such as porosity and water and chloride contents. For this purpose, tests introducing two electromagnetic methods, GPR and the capacitive technique, as well as the impact echo method, were run on 6 different concrete mixes containing various porosities, with 5 water content values and 3 chloride concentrations. 3. Methodology. As we know, concrete is widely used as a construction material because of its high strength Costra T1 main applications. Concrete a construction sera generally expected to give trouble-free service throughout its intended design life. However, these expectations are not realized in many constructions because of structural deficiency, material deterioration, unanticipated overloadings or physical damage, and thus civil structures like buildings, dams, bridges subjected to continuous deterioration over the years. For structural auditing, we have chosen a residential building situated at Kolhapur, and an investigation can be carried out in the following methods. A. Visual examination. B. Non-destructive testing. A. Steps of audit. In order to carry out structural audit, old RCC building is selected of age around 30 years. Steps involved in structural audit carried out are as follows. Step 1. Preparation of architectural and structural plan of the building. Architectural and structural plans are helpful in structural calculation, identifying or highlighting critical areas in the building. Step 2. Loading assumption. Making assumption of load based on the intended use of the building, i.e. whether it is commercial, residential. Finding which code requirement has been met. Step 3. Preliminary inspection of the building. This inspection involves A. Visual inspection. B. Tapping observation. Step 4. Field test. After highlighting critical area in the building, next step is to recommend the appropriate test to evaluate the structure, which may include like A. Destructive testing. B. Non-destructive testing. Step 5. Recommendation of remedial or retrofitting methods. Step 6. Preparation of structural audit report. 4. Visual inspection. A. Introduction. Visual testing is probably the most important of all non-destructive tests. It can often provide valuable information to the well-trained eye. Visual features may be related to workmanship, structural serviceability, and material deterioration, and it is particularly important that the engineer is able to differentiate between the various signs of distress which may be countered. These include, for instance, cracks, pop-outs, pulling, disintegration, color change, weathering, staining, surface blemishes, and lack of uniformity. Extensive information can be gathered from visual inspection to give a preliminary indication of the condition of the structure and allow formulation of a subsequent testing program. The visual inspection, however, should not be confined only to the structure being investigated. It should also include neighboring structures, the surrounding environment, and the climatic condition. This is probably the most difficult aspect of the whole structural investigation or any diagnostic works, since what appears obvious tone may not be so to another. The importance and benefits of a visual survey should not is underrated. Often the omission of what appears to be insignificant evidence can lead to a wrong conclusion being made. Thedvantagio fat trained I is best described by Sherlock Holmes when he wrote I Xenomorphania, but I have trained myself to notice what I see. B. Tools and equipments for visualization. An engineer carrying out a visual survey should be well equipped with tools to facilitate the inspection. These involve a host of common accessories such as measuring tape, rulers, markers, thermometers, anemometers, sandothers. Binoculars, telescopes, borescopes, and endoscopes, or the more expensive fiberscopes may be useful where access is difficult. A crack width microscope or a crack width gauge is useful, while a magnifying glass or portable microscope is handy for close-up examination. A good camera with the necessary zoom and micro lenses and other accessories, such as polarized filters, facilitates pictorial documentation of defects, and a portable color chart is helpful in identifying variation in the color of concrete. A complete set of relevant drawings showing plan views, elevations, and typical structural details allows recording of observations to be made. See general procedure for visualization. Before any visual test can be made, the engineer must peruse all relevant structural drawings, plans and elevations to become familiar with. Structure. Available documents must also be examined, and these include technical specification, past reports of tests or inspection made, construction records, details of materials used, methods and dates of construction, etc. The survey should be carried out systematically and cover the defects present, the current and past use of the structure, the condition of adjacent structure, recent environmental condition. All defects must be identified, the degree classified, similar to those used for fire-damaged concrete, and, where possible, the causes identified. The distribution and extent of defects need to be clearly recognized. For example, whether the defects are random or appear in a specific pattern, and whether the defect is confined to certain locations of members or is present all over the structure. Visual comparison of similar members is particularly valuable as a preliminary testing to determine the extent of the problems in such cases. A study of similar structures or other structures in the local area constructed with similar materials can also be helpful in providing case study evidence, particularly if those other structures vary in age from the one under investigation. There is a need to identify associated or accompanying defects, especially which particular defect predominates. Segregation or excessive bleeding at shutter joints may reflect problems with the concrete mix, as might plastic shrinkage, cracking, whereas honeycombing may be an indication of a low standard of construction workmanship. Lack of structural adequacy may show itself by excessive deflection or flexural cracking, and this may frequent lip theory zone for an in situ assessment of a structure. Long-term creep defections, thermal movements, or structural movements may cause distortion of door frames, cracking of windows or cracking of a structure or its finishes. Material deterioration is often indicated by surface cracking of the concrete, and examination of crack patterns may provide a preliminary indication of the cause. Systematic crack mapping is a valuable diagnostic exercise when determining the uses and progression of deterioration. Observation of concrete surface texture and color variations may be a useful guide to uniformity. Color change is a widely recognized indicator of the extent of fire damage. Visual inspection is not confined to the surface but may also include examination of bearings, expansion joints, drainage channels, and similar features of a structure. Any misuse of the structure can be identified when compared to the original designed purpose of the structure. An assessment may also need to be made of the particular environmental conditions to which each part of the structure has been exposed. In particular, the drying frequency and temperature variation that an element is subjected to should be recorded, because these factors influence various mechanisms of deterioration in concrete. For example, in marine structures it is important to identify the splash zone. Settlement of surrounding soil or geotechnical failures need to be recorded. Account must also take note of climatic and other external environmental factors at a location, since factors such as freeze-thaw conditions may be of considerable importance when assessing the cause of deterioration. A careful and detailed record of all observations should be made as the inspection proceeds. Drawings can be marked, colored, or shaded to indicate the local severity of each feature. Defects that commonly recording include 1. Cracking, which can vary widely in nature and style depending on the causative mechanism. 2. Surface pitting and spalling. 3. Surface staining. 4. Differential movements or displacements. 5. Surface voids. 6. Honeycombing. 7. Bleed marks. 8. Constructional and lift joints. 9. Exudation of efflorescence. D. Application of visual inspection. For existing structures, presence of some feature requiring further investigation is generally indicated by visual inspection, and it must be considered the single most important component of routine maintenance. It will also provide the basis for judgments relating to access and safety requirements when selecting test methods and test locations. As mentioned earlier, a visual inspection provides an initial indication of the condition of the concrete to allow the formulation of a subsequent testing program. It is also through such inspections that proper documentation of defects and features in the concrete structure can be effected. With a trained eye, visual inspection can reveal substantial information regarding the structures such as the construction methods, weathering, chemical attack, mechanical damage, physical deterioration, abuse, construction deficiencies, or faults, and many others. In this building is thoroughly inspected from flat to flat, noting racks, spells, crazing, seepage, etc. Highlighting critical area of investigation and repair. Same is marked on the plan of the building. Need of visual. 1. To inspection to recognize the types of structural defects. 2. To identify any signs of material deterioration. 3. To identify any signs of structural distress and deformation. 4. To identify any alteration and addition in the structure. Misuse this may result in overloading. F. Structural system of building. Substructure. settlement of columns or foundations, settlement of walls and floors, deflection and cracks in retaining wall, soil bearing capacity through trial pits or from adjacent soil data. Superstructure, materials used and framing system of structure, identification of the critical structural members like floating columns, transfer beams, slender members, rusting of exposed steel and its extent. Mention the status of all building elements like beams, slabs, columns, balconies, canopy, false ceiling, chaja, parapet, and railings with respect to parameters deflection, cracks, leakages and spalling of concrete. Likewise, verify the status of water tank, staircase, lift and lift machine room. V-field test. After highlighting criticality building next bestorkament the appropriate test to evaluate the structure which may include like 1. Destructive testing. 2. Non-destructive testing. 1. Destructive testing. Destructive testing are carried out to understand the specimen's failure, specimen's performance, or material behavior under different loads. These tests are generally much easier to carry out, yield more information, and are easier to interpret than non-destructive testing. Destructive testing is most suitable, and economic, for objects which will be mass-produced as the cost of destroying a small number of specimens is negligible. It is usually not economical to do destructive testing where only one or very few items are to be produced. Analyzing and documenting the destructive failure mode is often accomplished using a high-speed camera recording continuously until the failure is detected. Detecting the failure can be accomplished using a sound detector or stress gauge which produces a signal to trigger the high-speed camera. These high-speed cameras have advanced recording modeste capture il mostanotype destructive failure. After the failure the high-speed camera will stop recording. The capture images can be played back in slow motion showing precisely what happened before, during and after the destructive event, image by image. Some types of destructive testing are 1. Stress tests. 2. Hardness test. 3. Crash tests. 4. Metallographic tests. 2. Non-destructive testing. Non-destructive testing, NDT, is a wide group of analysis techniques used in science and technology industry to evaluate the properties of a material, component, or system without causing damage. The terms non-destructive examination, non-destructive inspection and non-destructive evaluation are also commonly used to describe this technology. Because NDT does not permanently alter the component being inspected, it is a highly valuable technique that can save both money and time in product evaluation, troubleshooting, and research. Analyzing and documenting a non-destructive failure mode can also be accomplished using a high-speed camera recording continuously, movie loop, until the failure is detected. Detecting the failure can be accomplished using a sound detector or stress gauge which produces a signal to trigger the high-speed camera. These high-speed cameras have advanced recording modes to capture non-destructive failures. After the failure the high-speed camera will stop recording. The capture images can be played back in slow motion showing precisely what happened before, during and after the non-destructive event, image by image. NDT tests are applicable in testing the condition of the bridges, highways, building. NDT allows users to determine following properties of the object. 1. Strength. 2. Durability. 3. Density. 4. Moisture content. 5. Elastic properties. 6. Extent of visible crack. The final benefit of non-destructive testing may be hard to quantify, but it's the most important of all. Knowing that your equipment is functioning the way it should, and that future accidents can be prevented with simple check UPS, adds years to the life of a bel ague. Non-destructive test. 1. Ultrasonic pulse velocity method. 2. Rebound hammer test. 3. Bar locator / cover meter. 6. Case study. Sister no. Description. Details. 1. Building name. Shri Vishwanath Co-Housing Society, Ward Kolhapur. 2. Date of starting structural audit. 23/11/2017. 3. Year of construction. 1979. 4. No of building. Total 7. A type 2 and O. B type 3 and O. C type 2 and O. 5. Area of plot. 4023.70 square m. 6. Existing floor area. 3760.30 square m. 7. Total built-up area. 4015.60 square m. 8. Structure. RCC framed structure. 9. Foundation. Simple footing, pile foundation. 10. Plaster. Cement plaster with dry distemper and waterproof cement paint. 11. Flooring. Rooms plain cement tiled. Kitchen 1.5-inch black catapastone. 12. Skirting dado. White glazed tiled 5-inch for all rooms. 13. Doors. Main entrance teak wood paneled. All internal doors Nova teak wood. Any other sustainable material paneled with MS angle frame. 14. Windows. MS glazed with 3/8-inch square bar SASA security bars. 15. Year of last repair. Generally 4 to 5 years ago. 16. Details of last repair. Structural repair. Roof or any other waterproofing. External finish, paint. Plumbing. None. Done for some of the buildings. Done for all buildings. Done for all buildings. 17. Plan and drawing. Architectural plan. Structural plan. Building plan. Yes. No. Yes. 18. Mode of inspection. Visual inspection. Field test, NDT. Yes. Yes. 1. Visual inspection of bindings. Results. Wing A. Leakage from slab. Diagonal cracks near opening. Dampness in walls and slab. Uneven settlement in flooring. Separation of balcony. Separation of balcony, gap. Separation of balcony. Wing B. Reinforcement is visible. Cover removal of slab. Diagonal cracks to wall. Major cracks to below of staircase cap. Leakage from pipes. Major leakage. Settlement of floor. Reinforcement is visible. Wing C. Slab detached out in balcony. Diagonal cracks above opening. Major dampness in wall. Major leakage. Major horizontal cracks above window. Plaster damage. Patches removed. 7. Remedial measures. Following corrective measures should be taken in order to enhance the life of the building structure. At the place of leakage and dampness. 1. Grouting. Grouting in civil engineering refers to the injection of pumpable materials into a soil or rock formation to change its physical characteristics. It is one of the ways in which groundwater can be controlled during civil engineering works. Grouting is suitable where soil permeability would create a heavy demand on pumping or where ground conditions mean it may be economically inefficient to bore wells. A close-up of a device description generated with high confidence. 2. Injection method. Typically, grouting is carried out as by driving pipes or boring holes into the ground, and then pumping the grout solution at high pressure through inserted tubes. The extent of grouting required for a particular area is determined through investigation of ground conditions and the calculation of a drilling pattern. This considers the size, spacing and depth of the holes required. The type of grout and the particular ground conditions will influence the spacing of the holes. 3. Grouting material. There are several different types of material used for grouting. A. Cement grouting. Cement, or cementitious grout, is used for grouting materials with a high permeability. Neat cement and water or a mixture of sand, 4 parts, to cement, 1 part, is the usual composition. Holes are bored in a radius around the area to be excavated before being injected with a thin grout, the viscosity of which is then increased by reducing the water-cement ratio. If required, secondary holes are bored between the primary holes to ensure the complete grouting of the area. B. Bentonite grouting. Bentonite is produced from clay which has thixotropic properties, meaning it forms a highly water-resistant gel which, when mixed with additives, can create a permanent barrier to water flow. This is used where soil particles are too small for cement grouting, most commonly to combat seepage in alluvial soils beneath the foundations of dams or other waterbound structures. C. Chemical grouting. Chemical grouting is used in soils of medium to coarse grading. Materials such as sodium silicate and calcium chloride are mixed together in liquid form and solidified into H. There are 2 main processes. 2-shot process. Pipes are driven into the ground. One chemical is injected followed by another, meaning that their action, and soil strengthening, is rapid. 1-shot process. This involves chemical mixing prior to injection, with the hardening being delayed by the composition. This allows for wider borehole spacing. Chemical grouting has the advantages of allowing economical spacing of boreholes, greater penetration of grout and more flexibility in terms of time of grouting. D. Chemical grouting. As opposed to chemical grouts, resin grouts have a very low viscosity which are able to penetrate fine sands. The type of resin used depends on the chemical content of the local water table and may result in different times for setting. Common types include tannin-based grouts, phenol formaldehyde, resorcinol formaldehyde. E. Resin grouting. Bitumen emulsion can serve as a suitable grouting material that can be injected into fine sands as an impermeable barrier to water. Soil strength will not be increased, but cut-off walls beneath dams and other waterbound structures can be formed effectively. A. Bitumen painting. Applying thin layer of bitumen on surface of wall externally to avoid the entry of rainwater. 4. Waterproofing. Waterproofing is the process of making an object or structure waterproof or water resistant so that it remains relatively unaffected by water or resisting the ingress of water under specified conditions. Such items may be used in wet environments or under water to specified depths. Water resistant and waterproof often refer to penetration of water in its liquid state and possibly under pressure, whereas damp-proof refers to resistance to humidity or dampness. Permeation of water vapor through a material or structure is reported as a moisture vapor transmission rate. The hulls of boats and ships were once waterproofed by applying tar or pitch. Modern items may be waterproofed by applying water-repellent coatings or by sealing seams with gaskets or O-rings. Waterproofing is used in reference to building structures, such as basements, decks, or wet areas, watercraft, canvas, clothing, raincoats or waders, electronic devices, and paper packaging, such as cartons for liquids. 5. Fiber wrapping. A fiber-reinforced polymer, CFRP, composite is defined as a polymer, plastic, matrix, either thermoset or thermoplastic, that is reinforced, combined, with a fiber or other reinforcing material with a sufficient aspect ratio to provide a discernible reinforcing function in one or more directions. FRP composites are different from traditional construction materials such as steel or aluminum. FRP composites are anisotropic whereas steel or aluminum is isotropic, uniform properties in all directions, independent of applied load. Therefore, FRP composite properties are directional, meaning that the best mechanical properties are in the direction of the fiber placement. Reinforced concrete buildings may be vulnerable to progressive collapse due to a lack of continuous reinforcement. Carbon fiber reinforced polymer, CFRP, may be used to retrofit existing reinforced concrete beams and provide the missing continuity needed to resist progressive collapse. A fiber reinforced polymer, FRP, composite is defined as a polymer, plastic, matrix, either thermoset or thermoplastic, that is reinforced, combined, with a fiber or other reinforcing material with a sufficient aspect ratio, length to thickness, to provide a discernible reinforcing function in one or more directions. 8. Conclusion. For framed structure, structural audit is necessary so that appropriate remedial measures can be recommended for all types of structural defects and damages. So that it continues to serve strength and serviceability requirement. For any structure it is necessary to carry out structural audit at least once in the 5 years. For structure older than 15 YEARS, structural audit should be carried out once in 3 YEARS. From above observation we conclude that even though heavy reinforcement is provided for the structural members and demand to capacity ratio is less than 1 for all structural members, reinforcement provided is in very bad condition and lost its strength due to corrosion. Due to corrosion there is reduction in the cross-section of the reinforcement resulting on deflection under their own weight, therefore unsafe to carry any further load. It is observed that main cause of damage of the structural members is due to corrosion and aging. Corrosion in structural members is observed due to dampness and leakage from the slabs, cracks in walls, etc. So the strength and serviceability of the building can be increased by taking necessary measures such as waterproofing slabs and walls to stop seepage of water into structural members so as to avoid further corrosion. Providing polymer mortar treatment, recasting of slab, etc. Acknowledgement. Based on the foregoing observations, we may deduce that, despite considerable reinforcing, the demand to capacity ratio for all structural elements is less than 1. Because to corrosion, the given reinforcement is in poor condition and has lost its strength. The cross-section of the reinforcement is reduced due to corrosion, resulting in deflection under their own weight, making them unable to support any further load.